Good afternoon, everybody. Sorry I can't be there today, but anyways, so for my Macrospace lesson plan, what I decided I wanted to do is that so growing up, I was always really big into Boy Scouts, and one thing that I did a lot of and quite enjoyed was orienteering. So basically, navigating using a map and compass, and I thought that this was a really good sort of macrospace activity because it lets you utilize some mathematic and trigonometrical principles while actually being outside and exploring a macrospace. And so, what I decided to do is I wanted to try to create some sort of lesson plan that was built around utilizing a compass. Now, for those of you who don't know how to use a orienteering compass, basically what you do is the compass is always pointing north, and what you can do is you can point the compass towards a landmark of some sort, and you can measure what the angle of that landmark is relative to your position when compared with magnetic north. And doing so, you can measure the angles of, well, any landmark that you can see, and then use those angles to triangulate your position. Figure out where those angles, figure out where the lines that come out of them intersect, that's where you are. So what I did is I decided to get a map of just the UMaine campus. I just went onto Google Earth and got a UMaine campus map. And then what I did is I took this map and I covered over it with just a white layer with two holes that kind of revealed two landmarks. So basically, the landmarks are spaced out as they would be on the actual world map, but you just can't see the rest of it. And I put some grid lines on there that match the magnetic north. And what I decided to do is my idea for it was to have students go out and go to various landmarks around these two revealed landmarks and basically just shoot declinations to those two landmarks. So I did the mall of UMaine campus, and I cleared out the bear statue over by the sports center, as well as the big tower on Stevens Hall, I believe it is. And so I went around on the mall and just shot declinations to these various points, and I wanted to see if I could build a map using just those angles. And doing so was actually pretty fun, and I decided to just kind of go out and just do it and kind of see what happened. And it actually turned out to have a lot more potential than I initially expected. That I'd initially hoped that it would basically allow students to just better understand and visualize angles in the real world and understand that you are always at some angle relative to an object, and that angle will always be different depending on where you are for different objects, and you can basically find your position as the intersection of two angles measured from two different objects. So I thought that would be kind of an interesting lesson, but then when I actually started to go out and do it, I found that there was a lot of mathematical principles kind of embedded inside of this. So for starters, the first landmark I decided to shoot declinations for was the big square cube thingy outside of Aubert. And so I started off and I measured to the bear structure, or the bear sculpture, and the bear was only at about 6 degrees or so. And this was easy to measure, but then when I actually tried to map it out onto my little blank worksheet, I found that, well, I can't just measure 6 degrees from the bear statue because that's going to be measuring in the wrong direction. And so what I needed to do is I needed to change the angle around 180 degrees or so. And in doing so, I realized that I'd actually just created a vertical angle by intersecting magnetic north with the declination that I shot. And so this was kind of cool because I feel like it did a really good job of showing that that two vertical angles are basically just one line at a consistent angle passing through another line, and so it's pretty easy to see that, oh, it's the same line just at different points, so it's going to be the same angle. So I thought that was really cool. Then when I tried measuring to the Stevens Tower on my compass, I found that the angle was 135 degrees. Now, to find the corresponding vertical angle, normally you just add 180 degrees onto this, but if I did that, then I got an angle of 315 degrees. And this was a problem to sketch out because my protractor doesn't go up this high. And so in order to draw this angle, I had to use coterminal angles. I had to understand that an angle of negative 45 degrees would provide the same vector as an angle of 315 degrees and would let me actually sketch things out. I tried another one, and I tried the library steps, and this actually helped to show that coterminal thing even more. That the library steps measured 354 degrees, to the bear statue, so it was almost directly below it. Now, at this point, if I just added 180 degrees onto this to get a vertical angle, I'd end up with an angle of 534 degrees. And this is definitely not something that I can put onto a protractor. And so, but seeing these angles in the real world, it's pretty easy to see, 534 degrees is, I mean, I'm still facing roughly the same direction as some other angles. And it's pretty easy for students to see that these angles can be adjusted and manipulated and to get a new direction. The last kind of fun lesson that I found was actually 100% by accident, but I thought it was really cool when I bumped into it, is I tried doing a measurement at the entrance to Little Hall. And Little Hall measured 342 degrees to the bear statue and 162 degrees to Stephen's Tower. I didn't notice this at the time, but when I was doing out the vertical angles and whatnot to be able to actually draw it out onto my map, I realized that 162 degrees and 342 degrees are exactly 180 degrees apart from each other. And so in this case, I actually couldn't draw the position of the entrance to Little Hall by using these two particular landmarks because it was just a line between them. I effectively only had one single line, and I couldn't find where that intersection was because it intersected at literally every point. So this was yeah, I just thought that this was really cool, and I think that on the whole, this activity it would get students out, and I think that they'd have some fun with it for starters. But I really do think it would do a good job of really showing a lot of these geometric principles and kind of helping students visualize how angles will interact with each other and with space in the world around it. Instead of just seeing angles as points on the paper, their angles are directions in the world that they're moving around in. So so that was my experiment. All right, well, have a good class, everyone.